Okay, so if you are new to having me as a teacher, then welcome to your first live stream. We'll do this for every test, and then we'll do this a bunch before the AP exam. Just an extra way for you to get a review session in, and you can interact with me live on it. So the way that will work is you can send me messages on Remind. If you're in my class, just use our Remind. If you're in Miss Belden's class, you can sign up for the Remind link that's right below me. And I will never send you messages, but you can send some to me. And then you can also chat on YouTube. So if you just go on YouTube and log into your account, you can chat there too. This is available in perpetuity on YouTube. So if you get cut off tonight, if you're exhausted because it's 9:30 and you just played Powder Puff, whatever, go to bed. You can watch this whenever over the weekend. The nice thing about the replay is that you can speed up, slow down, rewind, fast forward, but it's nice live so you can get questions answered if you have them. I try to hit the big points. If you need something more specifically retaught to you, that's a good thing to go see your teacher about, but we're going to hit the big ideas with this. I'm glad to see so many people on tonight, especially a couple of days before your test. It's awesome. So we're going to get started. So first things first, send me questions at any time, okay? You're never interrupting. I'm on about a 30 to 40 second lag behind or in front of you. So I might not get it. Like I may have moved on by the time I get it from you. So don't be offended if I don't respond right away. I will. So first thing I want to point out to you guys is that on your unit overview, you have these. These are your learning objectives, your learning targets. This should be used like a checklist. So if you want to know exactly what you need to be able to do on the test, look at this checklist and say, can I do each of one of these? Can I evaluate limits using a table? Can I evaluate limits from a graph? Can I do each of these things? If you can do these, you will be prepared for the test. The other thing I will say is, I know that you've been working on your con and you've been doing a great job on it. If you need more practice or you want different practice or you want AP style practice, you have 3 sets of review sheets in your unit overview, and the keys to all of those are on mine and Mrs. Belden's teacher site. So use those as resources, okay? You have so many resources to be prepared for the test. So use them and make sure that you're ready for, what is a college level test. So we're going to start small. We'll work our way up. We're going to go through everything from limits to IVT. And again, if you have questions, just send them. So we're going to start with limits from a graph. For the most part, we're pretty good at this. I just want to make sure we're aware of A, what different discontinuities are called, and B, how to find these. So limit as x approaches -2. Remember that this means from the left and from the right. So I would be looking at the x value of -2. From the left, I'm approaching the y value of 3. From the right, I'm approaching the y value of 3. And so what I wind up there is that my limit from the left and my limit from the right are both 3. Now notice that's not the value of the function there, and that's fine. That point is a removable discontinuity. Okay, in pre-calc you might have called it a hole. You're never going to hear us say that word, or you shouldn't. It's called a removable discontinuity in calculus. So if you see that, just think about a hole. It's been removed. So that would make your limit at -2, 3. For your limit at -3, if I look at that, notice I'm looking here. From the left, it's approaching -2. From the right, it's approaching -1. That limit does not exist because your high five would miss, right? The limit from the left and the limit from the right won't intersect each other. Now, what kind of a discontinuity is that? That should be a jump discontinuity, right? There is literally a jump in the graph. And then the limit of 3 from the left, so the limit as x approaches 3 from the left is -3. Now, DNE is fine to write. You do not need to write out does not exist. That's an accepted abbreviation. DNE is okay. Let's talk about a limit of a composition. So limit as x approaches -2 of g of f, given that g equals x cubed plus 1. So I'm going to do what I would always do with composition, which is start on the inside. So if I take the limit as x approaches -2 of f, my inside function, I'm going to look at -2, and my limit there we said was 3. Now what I'm going to do is use that as for my outer function. So now I'm going to take the limit as x approaches 3 of g of x, and I can say that that's 3 cubed plus 1. Notice, I didn't write x cubed plus 1 because I've substituted in, so you just want that 3 cubed plus 1. So this is 28. All right, now we're going to go into some more kind of AP style, a little less basic. So let's say I give you this. F of x is this piecewise function, x squared plus 1 and 1. And this is kind of interesting. So what it says is that everywhere except 1, that's what this means. At every value except 1, this is your function. So it's quadratic. At 1, it is just 1. So you have a hole in your graph at 1, and there's a point discontinuity there, or a removable discontinuity. So if it asks me for the limit as x approaches 1, what I need to consider is not the value at 1. I need to consider the limit from either side. So the limit as x approaches 1 from the left of f means consider the part to the left, which is this part. Even though it's on both sides, that's okay. It's to the left. So that would just be 4, right? 1 squared plus 3. Same thing if I take the limit as x approaches 1 to the right of f of x. And notice every time I'm not just writing limit as x approaches 1, I'm putting that f of x in there. And this is going to come out to be also 4. So my limit from the left and my limit from the right are both 4. That means my limit is 4. It doesn't matter that there's a hole. That 1 doesn't matter. That limit is 4. Okay, that's sort of a simpler piecewise function. Let's go to a little bit more complicated one. So this one has 3 pieces. So 3x squared if x is less than 0, 2 minus x if x is between 0 and 2, and radical x minus 2 if we're greater than 2. So 3 parts. Which is true? Let's look at these. So first one says the limit as x approaches 0 of f is 2. So I need to look at 0 from the left, which would be this piece, and from the right, which would be this piece. So my limit as x approaches 0 from the left of f, you're going to plug into that piece right there. So that would be 3. And the limit as x approaches 0 from the right of f of x would be 2. So this is definitely not true. My limit from the right is 2, but my limit from the left is 3, so it is not answer choice 1. And by the way, the AP exam loves these kind of questions where it will say to you, like, which of these are true? You will see these a ton. Next one, limit as x approaches 2 is 0. So we need to, again, look at from the left and from the right. So as x approaches 2, we're starting with this. As x approaches 2 on the right, we have that. So limit as x approaches 2 from the left is 0, 2 minus 2. Limit as x approaches 2 from the right, plug into that bottom part. That is square root of 2 minus 2, which is 0. So that is true. So my answer has to have 2 in it. So it can't be A, it can't be C, and it can't be E. So it's either B or D. Now, does the limit as x approaches 1 equal the limit as x approaches 6? This requires thinking about what part you're in. So limit as x approaches 1 is in this part. And that's a continuous function that's linear on that interval. So I don't need to do limit from the left, limit from the right. So limit as x approaches 1 of f of x is just going to be 1. Plug into 2 minus x. For limit as x approaches 6, I would have this. So limit as x approaches 6 of f of x is square root of 6 minus 2, or radical 4. So that's 2. Those are not the same, so it is not that. So that gives me my answer of B. All right, let's rev it up a little bit more. So now we're actually going to calculate some limits, not in a multiple choice question. We actually just need to calculate. So first thing I'm going to always look for is, can I directly substitute? It will save you time. It will save you hassle. Check it first every time. So if I take this one, the limit as x approaches 2, let's try direct substitution. In my denominator, I see I get 0. That doesn't automatically mean that I should start factoring. That could mean that it's a number over 0 and it's a vertical asymptote. Now, if I plug into the numerator, I get 4 plus, 4 plus 6 minus 10. And that actually would give me 0. So I get an indeterminate form. Now, here's what I never want to see. I never want to see that there, because 0 over 0 is not a number. So I don't want to put equals. I can say 0 over 0, or I could write indeterminate, but you cannot put equals 0 over 0 there. Now, that tells me 0 over 0 tells me go on and do more work. So carrying my limit on, because you're in calculus class, so you should be doing some calculus work, I've got the x minus 2 staying the same. And then this would be x plus 5x minus 2. Those cancel. Limit as x approaches 2 of x plus 5. And now I'm substituting in so I can drop my limit is just 7. Again, kind of starting simple. We'll rev our way up a little bit. Let's go to this one. So again, the first thing you should always be trying is direct sub. If I try direct sub, I get 0 over 0. Indeterminate, that's that word, right? And no equal sign there, because that's not a number. So now I'm going to do some algebra. So when you have a radical in there, the easiest thing to do is to multiply by the conjugate. So that just means keep the first and the last part the same, change the sign in the middle. So I'm going to keep those the same. And now I'm going to actually multiply. So for my numerator, remember that this is almost like a binomial times a binomial. So you're going to multiply out. So this is going to be the limit as x approaches 1 of x plus 3. Now it's going to be plus 2x plus 3, and it's going to be minus 2 square root of x plus 3. So those cancel. Minus 4 over, and good algebra in your denominator, keep that x minus 1 in parentheses, and then keep this separate. And the one thing I would always advise you to do is please don't try to multiply out the denominator, because what happens here is you wind up getting 3 minus 4, which coincidentally is minus 1. And so these cancel. And that's what you want. If you leave it in factored form, you're going to see what cancels more easily. So limit as x approaches 1 of 1 over radical x plus 3 plus 2. Now I'm substituting, so I drop my limit. So 1 over 4. All right, let's rev up a little further. So tangent of pi over 4, sine pi over 4, cos pi over 4, those we should know off the top of our head. So tangent of pi over 4 is 1, that gives me 0. Sine and cos at pi over 4 are equal, so that gives me 0. Again, I've got an indeterminate form. So now I'm going to do some simplifying, right? So let's see where I would start. Limit as x approaches pi over 4 of, there's no squared, so I would not go Pythagorean here. I would say this is sine x over cos x minus 1 over sine x minus cos x. Now, some people like to multiply through by the common denominator on the top and the bottom. You can do that. I kind of like just working from the top and then going to the bottom. It doesn't matter to me what you do, but I've seen more of you guys do this. So that's what I'm going to do, just because I think that's what you guys would do there. So what that gives me is limit as x approaches pi over 4 of, when you distribute this out, it's just sine x minus cos x over cos x times sine x minus cos x. And so I see that these cancel, right? I see that I get this a like factor, those cancel out, and so this is the limit, and you can put an equal sign there if you want because you're continuing your limit. Limit as x approaches pi over 4 of 1 over cos x. Now that is secant, so you could also think about this as the limit of secant. So pi over 4, cos of pi over 4 is radical 2 over 2, so this would be 2 over radical 2. And it's fine to leave your answer in that form. That's totally fine. You don't need to rationalize once you get up into calculus. Again, if you have questions as we go, send them, okay? Now, when I look at this one, I see that I get 0 over 0, and that's indeterminate. So let's try to do some simplifying. So limit as x approaches 0 of sine over cos over x. True. Did it help me? Maybe not a lot. So I'm just going to do a little bit of algebra, rearranging. So I'm going to make this sine over cos. And notice I'm writing the x's every time in there, right? I'm not just writing sine and cos. I'm writing sine x, cos x, times 1 over x. And what I can do here is I can say, well, that's actually the limit as x approaches 0 of sine x over x times 1 over cos x. Now, thing I never want to see you guys do here is I never want to see you go, oh, those cancel. Do those cancel? No, canceling means they divide to equal 1. Those don't divide to equal 1. I know that their limit is 1. I understand that. But they do not cancel, so don't do that because technically that would be incorrect algebra, right? So here I would say, okay, let's evaluate these limits. The limit of sine x over x as x approaches 0 is 1. That's one of the 2 special trig ones you should know. The limit as x approaches 0 of 1 over cos is 1 over 1. So this is just 1. So I know that these notation things can be annoying, but it's one of those things like in the end you can wind up losing points when you know what you're doing. So just be careful with it as you go. All right, multiple choice. This is straight off an AP exam. Let's look at this one. So limit as x approaches 1 of absolute value x minus 1 over 1 minus x. What I always test on these, before you do all the algebra of actually rewriting it as a piecewise function, what I would do is first actually see if you get indeterminate. Because if you got like a number over 0 here, what you would know is that that's a vertical asymptote, and all you would have to do is check whether it's approaching positive or negative infinity. So first, check that it's indeterminate, which you should be doing with every problem. So if I do that, I do get 0 over 0. Big surprise, right? And so I do need to rewrite this as a piecewise function. So quick review on that. You did this a lot in pre-calc. We've done it a lot this unit. But you're going to look at where the absolute value part has a 0. So that has a 0 at 1. And you're going to think, you don't really need to draw a sign chart here. That's going to tell you where this splits, okay? So this is going to be splitting x is less than 1, x is greater than 1. Technically, at x equals 1, it's not defined. So if you don't have an equal to sign there, it's okay. Now, let's think through this. When x is greater than 1, this expression is positive anyway. So absolute value doesn't need to change anything, so it would just be that. When x is less than 1, when x is less than 1, this expression would be negative, and so absolute value would have to change both of these signs. So that's what I wind up with there. So I'm going to simplify this down a little more. So this is actually equal to, in the numerator, that's just 1. You could rearrange that to be 1 minus x. So when x is less than 1, this equals 1. In the denominator, these are the opposite of each other. So what you could actually do here is factor out a negative 1 and make that x minus 1, and then they could cancel. So this is just negative 1 when x is greater than 1. So what is the limit as x approaches 1? Well, my limit from the left is positive 1. My limit from the right is negative 1. And so that limit is non-existent. If this was a free response, you would be writing out that information. Okay, last 2 on these, and then we're going to do some continuity stuff. So for this one, I see that it's my limit as x approaches infinity. So what I want to look at here is the dominant terms, right? The end behavior model. So I'm going to look at this in my numerator. The x to the 4th is dominant. In my denominator, the 2x cubed is dominant. So my end behavior model here is x to the 4th over 2x cubed, which is x over 2. So whatever this does, it's going to behave just like that. Okay? Now, on this one, the top dominates, which means it's going to keep growing and growing and growing Just like x over 2, that's just a line that keeps growing and growing and growing. So this limit does not exist. The top dominates, the limit does not exist. Okay, let's go to the next one. This one, a lot of people were missing on con, and I totally get why. It's tricky because of the negative infinity. So let's think about this. This is my dominant term in the top and my dominant term in the bottom. And what you need to do is kind of remember your signs here. So yeah, my end behavior model here does kind of look like 2x over 3x, right? But remember that the 2x in the numerator can never be negative, right? You're taking a square root, and our square root will wind up being negatives. We're working over the real number system. So it's almost more helpful to think about that as the absolute value of 2x. So now, thinking about plugging negative infinity into that, you would have positive in your numerator, but negative in your denominator. So even though, yeah, these are both growing at the same rate, and so you're going to divide your leading coefficients, this would be negative 2/3 because the top can't be negative, but the bottom can. And that's really tricky. All right, I'm going to pause a second. If you have any questions, send them. We're going to move on to continuity if we don't. Okay, let's move our lives on. All right, so this, again, straight off an AP exam, very common kind of question. So let f be defined by the function x squared minus a over x minus a for all x not equal to a. This is like what we did above. And for when x equals a. If f is continuous, remember what that means. Continuous means that f of a needs to equal the limit as x approaches a of f. You should be able to pull up that definition at the drop of a hat, okay? For all real numbers, what is the value of a? So here's how I would figure this out. And I know when it's a multiple choice, sometimes you can like guess and check, but I would want to see this kind of written out, especially if it was a free response. So let's look at this. Let's find the limit as x approaches a. And you could do it from the left or from the right. It doesn't really matter, but I'm going to do both because to be the most rigorous, we would want to do that. Now, if I look at this actual algebra here, this is x minus a, x plus a, and these would cancel. So I'm really just looking at the limit of x plus a. And so this would equal 2a. This would equal 2a. Substituting a in to that expression. Now, what I need is for that to equal f of a, which is 4. So, since those are both 2a, I know 2a needs to equal 4, so a has to equal 2. Okay, let's go to the next one. A little more complicated. Now I'm giving you a system, right? I'm giving you 2 variables. So, same idea. What we need to think about is, well, where might this not be continuous? So the issues are going to come up where these meet. So at -2, they meet. And then the other issue is going to come up at 1, because that's where those 2 pieces meet. So let's kind of consider those separately. So at -2, let's do our limit as x approaches -2 from the left of f. And the left-hand piece is the top piece. So that would be -6 minus a. And then the limit as x approaches -2 from the right of f of x, which would be 4 plus b. And f of -2, which is, oh, not 4, sorry, 8 plus b. And then f of -2, which is 8 plus b. So that's at -2. Now I'm going to deal with it at 1. So now I'm going to say, okay, what's my limit as x approaches 1 from the left of f? Limit as x approaches 1 from the right of f. And what's f of 1? So f of 1 is going to be in that middle piece. So that would be 2 plus b. That's also going to be my limit from the left of 1. And my limit from the right of 1 is 4. 5 minus 1. So I get this system now. So I know here that 2 plus b must equal 4, right? Oops, sorry, you can't see that. 2 plus b equals 4. So b is 2. Now what is a? Well, I know b, right? So I know that this and this must be equal. So negative 6 minus a equals 8 plus b. Negative 6 minus a equals 10. So a must equal 16. Negative 16, sorry. So you wind up with a system of equations. But the really key part for us to see from a calculus perspective is that you're doing limit from the left, limit from the right, value of the function, and setting those equal. All right, last thing we're going to talk about is intermediate value theorem, and then I'll hang out for questions. So IVT, big idea, right? If you have a continuous function on a closed interval, and I know it starts at one place and ends at another, if I pick any y value between those, it has to hit it at least once, right? And the big things to remember, continuous on the closed, and then your value needs to be between those points. So let's think about this. F is continuous on negative 2 to 7. So I see continuous on closed. Double thumbs up there. This is f of negative 2. This is f of 7. So my value needs to be between these y values, okay? So which of these is true? So first of all, I would say this f prime, this f with the apostrophe, you've never even seen. So it's probably not those. Now, f of 0 equals 0. Well, is that possible? Sure, it's possible. I don't know. I don't know what it equals at 0. I know it has to equal 0 at some point, but I don't know when. So it's not A. So that narrows it down to D and E. So for D and E, let's think about this. I know, just from reading it, and I know what IVT says, that my y values start at 5 and go down to negative 3. So I have to hit every value between 5 and negative 3. Let's see what this says. That f of c equals 0 for at least one c between negative 2 and 7. For f of c equals 0 for at least one c between negative 3 and 5. So the question is, like, which one of those is right? These are your y values. That's not the interval we're talking about. The interval we're talking about is between the x values. So what I want to pick here is D, because if we really thought about this graph, what this is saying is between negative 2 and 7, this starts at 5 and ends at negative 3. I don't know what it does in the middle. It could do whatever. But it's every value between negative 2 and 7. That's our interval. All right, last one, and this is one that definitely, maybe we'll do two more, we'll kind of see. This is one that trips people up, which is the explanation for IVT, okay? So looking at this, the table is given. The function h is given by h of x is f of g of negative 6, explained by there must be a value between 1 and 3 such that h of r equals negative 5. So I know this is IVT because it's telling me it's continuous, good, and I'm asking for a value between this x interval that equals a specific thing. So let's start with this. We know we want h to be negative 5. Negative 5 needs to be in our interval. So let's figure this out first. Let's find h of 1, and let's find h of 3. So those are kind of my endpoints of that interval. So h of 1, I'm going to do f of g of 1 minus 6, and f of g of 3 minus 6. So g of 1 is 2, and f of 2 is 9. So this is 3. And then for f of g of 3, g of 3 is 4, and f of 4 is negative 1. So negative 1 minus 6 is negative 7. So just think logically. If I start at 3 and end at negative 7, do I have to hit negative 5 at some point? Yeah, but that's not strong enough. So here's what I want to see in your explanations. I want to see, first of all, explain why. we know there should be. So since f and g are continuous, for all real numbers, right? H of x is continuous on the closed interval. So on 1, 3. That's my first part. And here's my second criteria. -5 is greater than h of 3, but less than h of 1, right? It's bigger than -7, but less than 3. And I actually want to see these. I don't want to see the actual numbers. So those are my two criteria. It's between them, and it's continuous. There exists, or there must be, that's a there exists symbol, an r on the interval from 1 to 3. I'm just copying this. There is a value r on the interval from 1 to 3 such that h of r equals -5. So the second part of your explanation, you're copying right from there. The first part is the really important part. I would make sure you can write a killer explanation of this. There are very few things I guarantee. I guarantee you will see that. And I guarantee you'll see it on the AP exam too. All right, last one, and then I'll take questions. You guys are so quiet tonight. All right, let f be a function given by f of x is x cubed minus 4x plus 2. Use IVT to show there is a root. We need to know what a root is. A root is where f of x equals 0. So it's really the same problem as above. It means show me that this has to equal 0, which means I want to kind of squeeze 0 between my boundaries. So first of all, let's find our boundaries. So let's find f of 0 and f of 1. So f of 0 is 2. F of 1 is 1 minus 4 plus 2. So -1. Does that logically have to equal 0? Well, it starts at 2 and ends at -1, right? It's got to switch signs in there somewhere. It's got to hit 0. So here's my explanation. Since f is continuous on 0, 1, and if you're wondering why it's continuous because it's a polynomial. And that's one of those things that we know. We know polynomials are continuous. So since f is continuous on 0, 1, and 0 is greater than f of 1, but less than f of 0, by IVT, or you can just say there must exist. By IVT, there exists a, let's just copy kind of what we had above. There exists a C on the open interval from 0 to 1 such that f of c equals 0. And I use c here because I'm talking about like a specific number. I'm not talking about f of x because x could be any value. I'm talking about a specific c. And that would be a perfect explanation. Okay, so that's pretty much what's covered on your first test. I'm going to hang out for a few minutes, see if you guys have more questions. But please remember all the resources you have. You have so many things available to you between Livestream, Khan Academy, you know, your whole review packet, all of that. So between that and Miss Belden and I, you guys have tons of people to bother and tons of help that you can get. So hopefully we feel prepared for this test. All right, I'll hang out for a minute and send any questions. Otherwise, I hope you guys have a good night. All right, last call. Okay, so somebody said, could we go over the limit as x approaches negative infinity again? So yeah, I'm actually just gonna make up a new question. Okay, so let's look at two different scenarios. So let's say that I have the limit as x approaches negative infinity of x squared plus 3x minus 1 over the square root of x to the fourth minus 2x plus 1. Okay, let's say I'm starting with this. So if I look at this, look at my own behavior model, I'm looking at x squared and I'm looking at the square root of x to the fourth as my dominant terms. So I'm going to look at this as x squared and kind of think about the bottom almost as x squared. The thing to remember is that your denominator can never be negative here because you're taking the square root. That's got to be of a real valued number. And so this is going to be, the denominator is going to be positive. So it can help you when you think about it, when you take it out of a square root, to almost throw it in absolute value bars because, you want it to be always positive. So it's a good reminder of it. Now, let's say I plug into this, right? If I do negative infinity squared over negative infinity squared, those kind of just wind up canceling each other out. And when you square it, it becomes positive anyway. So this becomes a positive over a positive. And so this limit would just equal 1 because I'm looking at my leading coefficients. And the big idea here is the numerator is always positive because it's squared. The denominator is always positive for two reasons, because it's squared and because of those absolute value that I put there to remind myself. And so because I'm dividing a positive over a positive, it's positive 1. Now let's say I had kind of the same scenario, but we're going to tweak it one little thing. So the limit as x approaches negative infinity of x cubed plus 7x over the square root of 9x to the 6th minus 1. Say we have that, right? So again, look at your dominant terms. And your end behavior model here is x cubed over square root of 9 is 3, square root of x to the 6 is x cubed. But the thing to remember here is that radical is never going to be negative, right? So I would throw some absolute value bars around that just to save yourself the headache, just so you remember that if you're getting stuck. So now think about evaluating this. If you plug in negative infinity, your numerator would be negative. Your denominator would be positive, right? And so even though, yes, they have the same exponents, you should divide your leading coefficients. All of that is true. It would be 1/3, but the numerator is positive or is negative because you have a negative to the third. The denominator is positive because it's a radical. And so that makes this negative 1/3. If that doesn't make sense still, send me another question. I'm hoping that brief summary kind of helps, but I'll hang out again if you have another question. So when you take something out of a radical like that, my best advice to you is to put it in absolute value bars, because then you won't forget, oh, it came from a radical, it can't be negative. Anything else? Guys, if you hung out with me this late on a Thursday night before you have school tomorrow and 4 days before your test, you're awesome. Thank you. Great questions. If you have more questions, send them to us, but you're going to rock it. Just make sure you're ready, and you guys will do great on your first Calc test. So good luck, and I will see you guys soon.